Hello and welcome back to California Geology. I am Dr. Robert Lopez. Today I want to talk about the San Andreas Fault System. And this system refers to a network of faults with predominantly right lateral strike slip that really accommodate the motion between the North American and Pacific plates. And in the Bay Area, there's a series of faults I want you to know about. So if we look at this map I have in here, the main one obviously is the San Andreas Fault, which comes through the Santa Cruz Mountains here and goes offshore here at basically Muscle Rock, just south of Pacifica. Then it goes across the Golden Gate here, and then it goes back on shore at Stinson Beach, Bolinas Bay here. It goes through Point Reyes and the Tamales Bay, and then goes right along Bodega Head there, and then it goes off towards Mendocino in the north there. And remember, there's the right lateral strike slip motion between the North American plates and the Pacific plates. And the other fault I want you to know about is really the only one that occurs, or at least it's important here, that's on the west side of the San Andreas Fault, and that's the San Gregorio Fault. So the San Gregorio Fault really, it used to be called the Monterey Bay Fault System, but now we know it comes on land here at Point Año Nuevo. State Park there. Then it skirts through Half Moon Bay, and then goes back offshore over near just by in Half Moon Bay area there. And then as we move to east of the San Andreas Fault, the two main ones are the Calaveras Fault, which starts down here to the south. It goes through Hollister, and then it kind of breaks out into this Green Valley and Concord faults up in here, but just know the Calaveras, it's an important one because it does have a potential for at least a magnitude 6.5 or greater earthquake. And remember in 2007 we had the magnitude 5 earthquake there near Alum Rock, now in November there. And then there's the all-important Hayward Fault. Remember I mentioned the Hayward Fault is the most important fault, or at least the most dangerous fault in the Bay Area, because it's the urban core of the East Bay. And this one's probably also has the highest percent probability of a magnitude 6.7 or greater earthquake in all the Bay Area, even more so than the San Andreas Fault. This one has really is overdue in terms of its earthquakes. And really it's a northern segment of the Hayward Fault, which includes this Rogers Creek Fault. And later on I'll talk about a new model for earthquake prediction that just came out in March of 2015 of this year. And it talks about how large magnitude earthquakes don't necessarily relieve all the strain energy that's been accumulated. They can transfer energy to other fault segments. So maybe a large earthquake here or up in the Rogers Creek Fault can generate or spawn a large earthquake on the Hayward Fault and maybe one on the San Andreas. So there could be sort of this domino type effect, which is a new interesting scenario for earthquakes in California. So we'll talk about that. Now, kind of looking at a little bit of the history of the San Andreas Fault, it really stems back to the 1906 San Francisco earthquake. And this massive geologic structure, it was really realized after that earthquake, because geologists realized that the fault ruptured for about over 260 miles, a huge amount of rupture. In fact, it was geologist G.K. Gilbert, who was actually went on one of the Powell expeditions down the Colorado River. But he investigated the fault 10 days after the earthquake, followed it, and found surface rupture from Bolinas Bay over by Stinson Beach. So Bolinas Bay would be right where the San Andreas Fault re-enters the land right here. So they found fault rupture from Bolinas Bay down to San Francisco, where there was evidence of probably more of a ground rupture, ground breakage there. And his work, along with others, noted that the large extent of the fault, the 1900 earthquake report, was the first milestone in the identification of the extent of the San Andreas Fault and the nature of these strike slip faults. So people realized that this fault line wasn't local. It's a major geologic feature that really covers the 2/3 of the state of California. Now, let's look at some major elements of the San Andreas Fault. So in Northern California, the two important faults besides the San Andreas are the Hayward and the Calaveras faults. And then if you go down into Southern California, there's one called the San Jacinto Fault, which is over near Palm Springs and Indio and those areas there. And then the Elsinore Fault, which is a little bit to the north west of that in Southern California. Those are segments that also occur in Southern California. And then we've already talked a little bit about the way faults move, but let's kind of repeat this a little bit here. And so when we talk about the rate of movement, there's two ways that the faults are going to move. One is this creep motion, where you get a more or less slow, continuous movement on the fault, averaging anywhere from a centimeter to about 3 centimeters per year. So that's a little bit from like a quarter of an inch to maybe about a little over an inch there. And creep is actually very uncommon. It's an unusual feature to have on faults. Yet in California we have two. Really, there's three, but two in the Bay Area. The Hayward and the Calaveras faults are creeping faults. The other one is the San Andreas Fault. The San Andreas Fault actually has a creeping section. It's from San Juan Bautista down all the way to Parkfield. And Parkfield, we'll talk about Parkfield here in a little bit. Parkfield is important because there's a big seismic array. Geologists have been really studying this area because it has repeated earthquakes over the last 100 and so years. And but anyways, that part of the San Andreas Fault from San Juan Bautista down to Parkfield. Parkfield is near Paso Robles. That's a creeping section of the San Andreas Fault. Now, in fact, on that section, there's a winery there south of Hollister, San Juan Bautista, called the De Rosa Winery today. But back then, it was called the New Albanin Winery. And in the 1950s, it was first discovered because this winery is built on the fault, and the building is literally being cracked in two. And here's an example of some creep motion. This is actually the Calaveras Fault. The Calaveras Fault goes basically right through here. Right, it goes right through here, through these people's homes, and it's torquing and offsetting this sidewalk, right, where this side is moving this way and this side is moving this way, right? So there's some offset creep motion. There are homes that are built on the Calaveras Fault, and they're literally being cracked in half. Now, the other type of motion is this long-term slip rate, and we talked a little bit about this already. And the long-term slip rate is also called the stick slip, where the fault is locked in over many years, hundreds of years, and then suddenly it slips, moving several meters in a minute or less, or sometimes even a little bit longer. And for example, the 1906 San Francisco earthquake in Point Reyes Peninsula, so it happened, actually the epicenter was just offshore the Golden Gate, but a good place to see offset from that earthquake was at Point Reyes Peninsula, just north of San Francisco. And note that there was 4.7 meters of offset that happened basically. This was anywhere from 45 to 60 seconds of shaking. So in a minute, there was 14 feet of offset. And note that we're going to use centimeters later on, so that's really 470 centimeters that were offset. And that earthquake was about 109 years ago. So if we kind of do the averaging, we see that over 109 years, if we take remember the rate's going to be the 470 centimeters over those 109 years. Well, you get the 4.3 centimeters per year, right? Through studies at Skinner Ranch, Skinner Ranch is also up at Point Reyes, and your book talks about how they look at these stream deposits that were offset, and they did some carbon dating on the stream deposits, and they figured out in the past 1,800 years that the San Andreas Fault, at least in this area of Northern California, has a rate between 2.1 and 2.7 centimeters per year. And so that's actually a little bit slower than what we're getting here, which means that this fault has relieved, this 4.3 centimeters per year has relieved quite a bit of strain energy, and the fault is still accumulating strain. So in other words, it's not ready it's not ready to give another earthquake, at least not for a little while. And so let's see how we can figure out when to expect the next earthquake. So geologists also use this long-term slip rate for other reasons. So two other important reasons is one, it tells us about the history of motion along this plate boundary. Is it creeping motion, or is it going to be this long-term slip rate, and how often and how big the earthquakes, how much slip? Is it 4 meters or 6 meters? So we can tell at least along different sections of the fault. Then the other one that's important, if we can figure out the long-term slip rate, like we've done here, we figured out it to be 2.1 to 2.7 centimeters a year, then we can find segments that lag behind that long-term slip rate, and those are the locked segments that are overdue. So this particular section of the San Andreas Fault is still accumulating strain. So that's the one up by Point Reyes Peninsula, where the 1906 earthquake epicenter occurred. And so we can actually do a little calculation, and this is called a recurrence interval. So how often would we expect to have a magnitude 7.9 earthquake in the San Francisco region, north of San Francisco, along that part of the fault? And the way we do it, we take the slip in the fault during that earthquake, which was 470 centimeters, right, or 4.7 meters, and we divide it by the average slip on that fault for that particular area of the fault, and we figured out it's anywhere from 2.1 to 2.7 centimeters per year. So once we reach those numbers, then we're accumulating strain, and we can have another earthquake of that magnitude. And so if we do it over 2.1 centimeters a year, then the recurrence interval is every 224 years. If the fault is moving at 2.7 centimeters per year, which is in that range, then it can happen every 174 years. So we're still a little ways out for a large magnitude earthquake, at least in north of San Francisco, which means that other parts of the San Andreas Fault can still be locked in. And so, in fact, we'll talk about in the next section here.